Keep questioning the balance. Okay, let's unpack this. We are diving deep today into what might be the highest stakes engineering challenge humanity has ever really faced: planetary defense. And forget the dramatic movie tropes. We're looking at the highly complex real-world effort to protect Earth. Not with, massive missiles, but with precision orbital mechanics and kinetic impactors.
It's truly a watershed moment in space history, and I think you, our listener, will likely remember the spectacular success of NASA's DART mission.
The Double Asteroid Redirection Test Track.
Exactly. That was the moment we proved we could, in fact, hit a very small target in deep space and measurably change its trajectory. It was a massive foundational success for the whole concept of kinetic deflection.
But a successful collision is only the first chapter in this story. I mean, to be truly prepared, we can't just rely on a one-off successful punch. We need validation.
That's the key word.
We need the quantifiable data to turn a scientific proof of concept into a reliable, repeatable engineering tool. And that is the singular critical mission of the European Space Agency's incredible spacecraft, Hera.
Right. And Hera is so much more than just a post-impact cleanup crew. It is the world's first dedicated validation mission designed to understand the fundamental physics that, underpinned DART's success. It's the cornerstone mission of ESA's new and vital space safety program.
And its destination is the binary asteroid system, 65803 Didymos.
Yes, where its little moon, Dimorphos, now bears the scar of that 2022 collision.
So our mission today is to become expert witnesses to this validation process. We need to go back and really understand the fraught history of this project, how it nearly died before it was resurrected as Hera.
It is a very close call.
And then we have to analyze exactly what instruments this incredibly sophisticated spacecraft is carrying, because they're designed not just to look at the crater, but to literally, X-ray the asteroid's internal structure.
In a way, yes. It's a kind of radar X-ray. And this knowledge is what separates an educated guess from a guaranteed planetary protection strategy. The difference between DART and Hera is, it's like the difference between proving a gun fires and proving exactly how powerful the bullet is. We're moving from just observing deflection to scientifically validating how and why that deflection works so efficiently.
And that transition is what makes this deep dive so crucial to understanding humanity's future in space. The story of Hera, it doesn't really begin in a lab in 2019. It starts much earlier, rooted in a concept of global collaboration.
Right.
The initial joint concept established way back in 2013 was known as AIDA.
AIDA, the Asteroid Impact and Deflection Assessment.
So what was that?
AIDA was a beautiful two-pronged approach. It really showcased international cooperation at the highest level of space science.
And it was designed to target the Didymos system from the very beginning.
From the start. And that was because its binary nature. A large asteroid, Didymos, with a smaller moonlet, Dimorphos, orbiting it, that makes measuring the impact effects much easier. Well, if you change Dimorphos' orbit around Didymos, that period change is quickly and clearly measurable from Earth. It's much easier than trying to see a tiny change in the trajectory of a single asteroid against the background of space.
Makes sense. And the roles in AIDA were clearly defined, right?
Oh, very clearly. NASA was responsible for the muscle, the DART impactor itself, the thing that would accelerate and smash into Dimorphos.
And ESA's role was the brain.
The brain, exactly. The AIM, or Asteroid Impact Mission Orbiter. AIM's job was, arguably the most scientifically critical part of AIDA. It was supposed to arrive at Didymos first to provide the definitive before picture.
So it would measure everything.
Yeah.
The mass, shape, rotation.
Yeah.
All of it.
All of it. The surface composition of Dimorphos before the collision. Then it would witness the impact in real time and monitor the immediate aftermath.
That would have been amazing data.
It would have allowed scientists to calculate the momentum transfer with just unprecedented accuracy. That twin mission approach. It was the ideal way to capture the entire physical process.
But space missions, especially ones that require complex international funding, they rarely go according to the ideal plan.
Unfortunately, no. Despite the technical readiness of the concept, the AIDA plan hit a catastrophic financial snag. Towards the end of 2016, ESA announced it had to abandon the development of the AIM orbiter.
That must have been a devastating setback for the whole planetary defense community. Why specifically did AIM get grounded?
It really came down to insufficient financial support from ESA's member states.
Money, again.
It's almost always money. While the technical value was, universally recognized, securing the significant financial commitments, we're talking millions of euros that were needed to develop and fly a deep space orbiter in that time frame, it just proved impossible.
Planetary defense wasn't a high enough priority back then.
For some nations, no, it was still viewed as a lower priority compared to other space science or, say, telecommunications endeavors. Without that sufficient backing, the mission was shelved.
So ESA dropped out of the partnership, but NASA kept DART going. I have to wonder, if AIM was supposed to provide the vital before and during measurements, why did DART proceed solo? Wouldn't that leave a massive gap in the physics data?
That's a great question, and it speaks to the high priority of proving the kinetic concept itself. NASA scientists recognized that the ability to actually perform the maneuver to autonomously navigate, hit that small target, and demonstrate any orbital change was paramount.
So they decided a partial success was better than no mission at all.
Exactly. They relied on terrestrial observatories to partially take over the measuring role, and those teams did perform impressively well. They were able to measure the change in orbital period after the impact.
But they couldn't get the intimate details, could they?
No. I mean, ground-based telescopes, even the very largest ones, they just cannot provide the spatial resolution needed to map the crater or measure the precise volume of ejected material or, crucially, determine the exact mass and internal structure of that small, irregularly shaped dimorphous moonlet.
So we proved that we could do it, but we left that why it worked so well largely unanswered.
Perfectly put.
And speaking of DART's success, let's just briefly set the scene for Hera's arrival. DART launched in November 2021, and in a really incredible display of astronomical precision, collided with Dimorphos on September 26, 2022.
And smashed into it at a velocity of about 6.6 kilometers per second.
Just a staggering speed.
It was a truly spectacular event. And we weren't entirely without close-up documentation thanks to the Italian space agency's Liscia cube.
Right, the little nanosatellite.
Yes, this small nanosatellite deployed by DART just before impact, it zipped past and documented the first 100 seconds or so. It captured these incredible images of the massive plume of ejected debris.
And the debris plume, as we now know, was far more significant than anyone predicted.
Far more. But the exact physics remained a mystery. And that mystery, that gap in crucial scientific data, led directly to the renaissance of the European contribution.
So the mission was reborn.
Precisely. In the aftermath of AIM's cancellation, ESA realized the profound nature of the data they were missing. So in 2017, they decided to resume studies, which ultimately led to the formal proposal and creation of the Hera Mission.
Named after the Greek goddess.
Consort of Zeus, yes. And Hera was designed specifically as the post-impact analyst, aiming to fulfill all of the original AIM objectives that ground-based instruments just couldn't touch.
So it was reborn not as the before orbiter, but as the after investigator.
Yes, and that required a far more advanced, more specialized payload. Hera was finally approved by the ESA Ministerial Council in November 2019. That really secured its place as the key validator for the space safety program.
And the money finally came through.
The money came through. The construction contract, awarded to a consortium led by OHB in September 2020, came in at a significant 129.4 million euros. This was a statement. Planetary defense is now a non-negotiable part of our long-term strategy.
You know, what's great about this historical context is that Hera is, in a way, fundamentally a stronger, more specialized mission because it missed the before picture.
How do you mean?
It forced its designers to include technology, like the penetrating radar we'll talk about, to reconstruct the asteroid's internal state after the impact.
That's a key observation. The constraints of the timeline forced innovation, ensuring that Hera is now carrying the necessary tools to answer the question DART left hanging. Not if we can do it, but how reliably we can do it, regardless of the asteroid's specific material properties.
Here's where it gets really interesting. DART was a spectacular shot, but Hera has to analyze the wound and write the medical report. Its core objective is scientific validation.
Absolutely.
So what scientific question is Hera primarily designed to answer?
The absolute primary objective is the planetary defense validation itself. We know DART changed Dimorphos' orbital period by 33 minutes.
Which was huge, right?
Right.
Way more than they expected.
Hugely more. It was significantly greater than the 7 to 10 minutes predicted by the initial models. And this deflection factor is quantified using what scientists call the momentum transfer enhancement factor, or the beta factor.
Let's pause on that beta factor, because that feels like the scientific heart of the mission. What exactly does it represent, And why did DART's performance confuse us?
The beta factor is essentially a ratio. It's the ratio of the total momentum actually transferred to the asteroid versus the initial momentum of the impacting spacecraft, DART.
Okay.
So if the asteroid were a monolithic, solid body like a bowling ball, the beta factor would be close to 1. The total deflection would just be the momentum of the spacecraft itself pushing it.
But DART's factor was estimated to be much higher, maybe closer to 3 to 5.
Exactly. Which means something else added momentum to the target.
The ejecta, the debris.
That something else was the colossal cloud of ejected debris, the shattered rock and dust streaming away from the impact site. When DART hit Dimorphos, it pulverized a massive amount of material. As this material rocketed away from the surface, it provided a significant secondary impulse, like a massive short-lived rocket engine firing on the opposite side of the impact site.
So the debris plume provided the majority of the overall deflection.
The vast majority. And if that ejecta plume provides the lion's share of deflection, we need to know the physics controlling it. Was it the low gravity, the material composition?
That's what Hera has to find out.
Precisely. Hera needs to determine how this efficiency, the beta factor, is dependent on the target's material properties. If an asteroid is dense and solid, a monolith, the ejecta plume might be minimal, low beta factor. But if it's a highly porous rubble pile,
A collection of weakly bound rocks and dust, riddled with internal voids.
then the impact will shatter and launch far more material, resulting in a high beta factor. This porosity, this internal structure, is the key variable that Hera is going to measure.
So we're not just studying how hard DART hit, we're studying the physical consequences of hitting a cosmic sandcastle versus a solid marble.
That's a perfect analogy. And furthermore, Hera has to analyze the energy partitioning. What proportion of DART's kinetic energy was absorbed by internal fragmentation and restructuring versus the kinetic energy carried away by that crucial ejected debris cloud?
Understanding that balance is the difference between a random success and a predictable engineered safety solution.
Absolutely.
And moving beyond just the defense validation, the mission also has enormous scientific objectives. We've never studied a binary asteroid up close after a human intervention.
No, never. The scientific bounty is huge. It starts with mapping Dimorphos. Hera will map the entire surface of the moonlet with a spatial resolution of a few meters.
But for the crater itself,
For the crater, it will focus its highest resolution imagery down to a razor-sharp 10 centimeters on the immediate vicinity of the impact.
10 centimeters. That means you can literally look at the scatter pattern of the ejecta and measure the size of individual chunks of rock that were launched into space.
A level of detail that is absolutely impossible from Earth. Secondly, mass measurement is paramount. To calculate that beta factor accurately, you need both sides of the equation. We need an extremely accurate, independent estimate of Dimorphos's mass.
And Hera is designed to provide this high-precision mass calculation.
Yes, through radioscience, which we'll get into. And the third major scientific objective, which is really the most innovative part of the mission, is characterizing the internal structure.
Getting beyond just guessing if it's a rubble pile.
To knowing definitively what's beneath the surface. Characterizing the subsurface and internal structure is where Hera truly breaks new ground. It is taking instruments specifically designed to probe the interior of a tiny celestial body that has never been done before.
Finally, the technological objectives. Hera isn't just a science vessel, it's a testbed for future deep space exploration.
Definitely. Especially for autonomous navigation around tiny, low-gravity objects.
The self-driving space car.
In a way, yes. The degree of independence the spacecraft must exhibit is just fascinating. It's operating millions of kilometers away. Radio signals take minutes to travel. So Hera is running guidance software that processes data from multiple sensors, its cameras, altimeters, to construct a continuous 3D model of its surroundings.
And it uses that model to independently define and adjust a safe trajectory.
A safe trajectory around a small asteroid, anticipating potential gravitational perturbations. It's basically training to be a fully self-driving space vehicle, capable of maneuvering in an environment where gravity is negligible and tiny errors can lead to immediate disaster.
Wow.
And the second major tech objective is proving that miniature science platforms are viable deep space assets. Hera is demonstrating the deployment of and continuous communication with its two tiny 12-kilogram CubeSats in the interplanetary environment.
Getting those miniature labs to function effectively millions of kilometers from Earth is a massive step forward for cost-effective space exploration.
So now that we fully appreciate the stakes, Let's trace Hera's journey since it left Earth, because the mission began with a few dramatic twists right off the launch pad. The spacecraft lifted off on October 7, 2024.
And its launch was far from routine, right?
Yeah.
Using a Falcon 9 rocket, but with some unusual constraints.
It was a logistical scramble. Hera needed to use Space Launch Complex 40, SLC-40, at Cape Canaveral. Now, SLC-40 is typically used for Starlink and commercial launches.
And the prime site was busy.
Exactly. The prime site for these complex orbital injections, Launch Complex 39A, was tied up preparing for the imminent launch of NASA's Europa Clipper mission. Launch schedules are rigid, and Hera had to adapt.
I recall hearing about an issue with the Falcon 9 booster itself, too. That must have added to the tension.
It did. The launch occurred while the Falcon 9 fleet was technically under a temporary grounding order. There was a mishap, second stage deorbit burn issue, during the preceding Crew 9 mission.
So how did they get permission to launch?
Well, because Hera was destined for a unique heliocentric orbit, an orbit around the sun, it posed a different risk profile. So the FAA granted a special waiver, recognizing the critical nature of the planetary defense mission.
So it took off as an exceptional mission, both scientifically and logistically, and the booster played its part.
Absolutely. The booster they used was highly flight-proven. It had already completed 22 previous missions. And to ensure Hera achieved the precise escape velocity it needed, the decision was made to expend the booster.
So they sacrificed recovery for performance.
They prioritized the mission's velocity requirements, yes.
Moving past the hectic launch, what were the first operational steps Hera took in deep space?
Within days of launch, while it was already over 1 million kilometers from Earth, Hera began rigorous testing of its main sensor suite. It activated the asteroid framing cameras, the thermal infrared imager, and the Hyperscout H imager.
And they pointed them back home.
They did. They pointed them back at Earth and the Moon, using them as massive, known calibration targets. This tested their sensitivity and accuracy at extreme range, which is crucial for later small-body tracking.
And the CubeSats, those miniature deep space explorers, were also given an early checkup.
Yes. Also in October 2024, the two CubeSats, Milani and Juventus, were briefly powered up. This was a critical technological proof point for ESA, confirming they could establish stable communications and confirm the health of these 12-kilogram assets.
And that was a first for ESA, right?
The first time ESA had successfully commanded and operated CubeSats in interplanetary space, a huge milestone.
And to set up the trajectory for the asteroid belt, Hera needed a massive boost. That meant the Mars Gravity Assist.
That gravity assist was the centerpiece of the cruise phase. After some preliminary burns, Hera performed its major deep space maneuver on October 27, 2024, firing its propulsion system for a full 100 minutes.
A 100-minute burn.
A 100-minute burn. It changed its velocity by 146 meters per second, putting it on course for that critical rendezvous with Mars.
Tell us about that crucial gravity assist, which happened in March 2025.
The assist was executed on March 12, 2025. Hera swooped in, passing within 5,000 kilometers of the Martian surface. That interaction provided the necessary gravitational slingshot.
Using Mars gravity to save fuel.
Exactly. It increased the spacecraft's velocity and shifted its orbital plane towards the main asteroid belt, all while conserving precious fuel.
But the team was smart. They didn't waste the opportunity. They used the flyby to perform a fantastic side mission involving Deimos.
It was an excellent piece of opportunistic science and engineering. As it approached Mars, Hera diverted slightly to observe Deimos, Mars's smaller, highly irregular moon. It imaged Deimos from a distance of 1,000 kilometers, with a closest approach of only 300 kilometers.
And that gave us invaluable new data on a P-type asteroid.
A very primitive, carbonaceous object that's notoriously difficult to image from Earth.
And maybe more importantly, that flyby was the ultimate stress test for the spacecraft's self-driving brain.
Absolutely. The main objective of the Deimos Pass wasn't just pretty pictures, it was a comprehensive technology test. Hera's autonomous navigation software had to autonomously lock on to specific, subtle Martian features, impact craters, surface textures.
To practice for the main event.
By tracking those features precisely as the spacecraft sped past, the system fully tested the complex algorithms it will need to navigate the tiny, chaotic gravity field of the Deimos system years later. It was practice for the big game.
So once past Mars, Hera settled into the main asteroid belt cruise phase, continuing to calibrate its sophisticated instruments.
Indeed. The AFC cameras and spectral imagers had to prove their tracking capabilities. This involved sighting known asteroids like 1126, Otero, and 18805, Kelly from millions of kilometers away. This calibration ensures that when Hera begins tracking Didymos, its instruments are perfectly tuned.
And then came a completely unexpected cosmic event involving a visitor from outside our solar system.
This was a truly unique encounter in late 2025. Between October 25 and November 1st, Hera found itself passing directly through the extended cometary tail of the third known interstellar object, the comet designated 3 Iates.
Wow, crossing the wake of a cosmic tourist.
It's a scientific lottery win. While not a planned observation, the potential for Hera's instruments, particularly the dust sensors on the CubeSats, to analyze the composition of material originating from another star system is a monumental, if opportunistic, scientific bonus.
So after this eventful and successful cruise, the destination is finally in sight.
When does Hera get to work?
Due to the precision of the trajectory and the success of the maneuvers, the mission team was able to announce that Hera is slightly ahead of schedule. It's now projected to arrive at the Didymos system in November 2026.
A month earlier than originally planned.
A month early. The real science is about to begin.
Let's talk about the machinery that enables this deep dive. Hera itself is a remarkably robust piece of engineering. A box-shaped main bus. Right, about 1.6 by 1.6 by 1.7 meters. 2 large solar panels, a high-gain dish for communication. All told, its launch mass was over a ton, 1,128 kilograms.
And its propulsion system is key to its success near a low-gravity body.
Absolutely. It uses bipropellant chemical thrusters, which offer a total delta V, that's the capacity for velocity change, of about 1,300 meters per second. That large reserve is essential for the precise, frequent maneuvers needed to maintain a stable orbit around tiny Dimorphos.
An orbit where even sunlight can push you around.
Exactly. Solar radiation pressure can significantly affect the spacecraft's trajectory.
So let's look at the primary science payload. The main instruments, Hera's high-resolution eyes and hyper-accurate rulers.
First up, the core imaging system, the asteroid framing cameras, AFC. There are 2 redundant, identical cameras using the faint star sensor technology.
And they do 2 jobs.
2 jobs, yes. They provide the baseline physical characteristics of the surface, but more importantly, they are crucial for providing guidance data to the autonomous navigation software. Their spatial resolution is highly advanced.
How advanced?
They can achieve 1-meter resolution when Hera is still 10 kilometers away from the target. This allows the mission planners to construct extremely accurate 3D shape models very early in the rendezvous phase.
Next is the planetary altimeter, HAL-ELT. Why is a laser altimeter so critical when orbiting a body that barely has any gravity?
HAL-ELT is essentially Hera's independent distance monitor. It's a micro-lidar system. Near a body with practically no gravity, calculating your position based solely on gravity models is unreliable. You need constant, high-precision distance measurements.
And PAL-T provides that?
It provides altitude accuracy of 0.5 meter, feeding that data directly into the attitude guidance system to ensure Hera doesn't drift away, or worse, crash.
We also have 2 spectral tools that tell us about the asteroid's surface composition and temperature.
We do. First, HyperScout H. That's the hyperspectral imager. It captures images across 25 distinct spectral bands in the visible and near-infrared light. This helps us characterize the distribution of minerals on the surface.
And then we have the contribution from JAX, the Japanese Space Agency.
That's the thermal infrared imager. TRI observes the thermal output in the 714 micron range using 6 specialized filters.
And why is temperature so important?
Because it tells us about the asteroid's thermal inertia. A highly porous surface, like a rubble pile, heats up and cools down much faster than a solid rock. TRI measurements are a key indicator of surface porosity and help us cross-reference the internal structure data.
Okay, finally, the most non-visual but maybe the most important measurement. X-band radio science, XDST. This is how we get the mass data for the beta factor.
This technique is just exquisite. It leverages the precision of Earth-based deep space tracking stations. As Hera orbits Dimorphos, the tiny gravitational tugs from the asteroid slightly perturb the spacecraft's velocity.
A very slight change.
Incredibly slight. But this tiny change in velocity causes a measurable shift in the radio frequency, the Doppler effect, as the signal travels back to Earth. By meticulously tracking these subtle frequency changes, scientists can calculate the exact mass of both Didymos and Dimorphos.
And without that mass, the whole beta factor calculation falls apart.
It's meaningless. The measurement is absolutely foundational.
Now let's talk about the true innovators. The two CubeSats, Milani and Juventus. These aren't throwaways. They are essential, dedicated field labs.
They really are. Both are 6U XL nanosatellites about the size of a shoebox, weighing 12 kilograms each. They gather data in orbits that Hera can't safely sustain, and they act as part of the radio science experiment.
Let's start with Juventus, the geophysical specialist. It carries the instrument designed to answer that deep question of internal structure.
Juventus is the key to unlocking the rubble pile mystery. Its primary instrument is the Jura radar, operating at a frequency of 50-70 megahertz. This is revolutionary.
The first of its kind.
The first radar system designed specifically to penetrate and image the inner layers of an asteroid. It uses two 1.5-meter-long dipole antennas to transmit radio signals that reflect off internal boundaries, voids, fractures, buried large fragments.
So instead of just seeing the impact crater on the surface, Jura will actually see the structural damage inside the asteroid caused by DART.
Precisely. Or maybe the pre-existing structure that made it so fragile in the first place. It aims for a spatial resolution of 10 to 15 meters within the asteroid. This data is the direct link we need to confirm that high porosity leads to high deflection efficiency.
And its end-of-mission plan is one of the most exciting.
Oh, yes. After its orbital observations are complete, Juventus is slated to attempt a landing on Dimorphos. It's a sacrifice maneuver.
And it has accelerometers.
It does. So the moment of impact and the subsequent movement, whether it bounces, sinks, shatters, will provide the last unique piece of data, the direct mechanical properties of the asteroid's surface.
Moving on to Milani, named after the pioneering Italian scientist Andrea Milani. Its specialty is surface composition.
Milani is focused on chemical mapping and the dust environment. Its star instrument is the Aspect Hyperspectral Imaging Spectrometer, and this is far more powerful than the imager on the main bus. It operates across 72 channels.
72 channels. What does that buy us scientifically?
It allows for incredibly fine discrimination between different materials. A regular camera sees 3 primary colors. Aspect sees 72 shades of color, allowing scientists to differentiate subtle compositional differences between various types of silicates, minerals, and organic materials.
Creating definitive compositional maps.
Exactly. And its second tool is the Vista thermogravimeter. This device is specialized in detecting fine dust particles that might be lingering around the asteroid. And crucially, it will also search for volatiles like traces of water, ice, and light organic materials, providing a snapshot of the material history of this unique body. So, with this whole suite of hardware, from the radar that peers within to the spectrometers that analyze composition, Hera is set for its grand arrival in November 2026.
Which will be a historic first.
The first mission ever to make a dedicated rendezvous with the binary asteroid system.
And the investigation is a marathon, not a sprint. We're looking at a carefully structured 6-month campaign broken down into 5 distinct phases.
Yes, that 6-month timeline is tightly managed to ensure data redundancy and safety. The mission logically progresses from far-field assessment to high-resolution contact investigation.
Phase 1 is early characterization, lasting about 6 weeks. What are the key priorities there?
In Phase 1, Hera maintains a safe, distant orbit. The focus is establishing the fundamentals, determining the global shape models, fine-tuning the mass and gravity characteristics with radio science, and establishing the thermal and dynamical properties of both asteroids.
The foundational data is vital because it informs every subsequent close-up trajectory.
It does. If the shape or mass is different than expected, the entire close approach plan must be adjusted.
Once they have a stable baseline, Phase 2 is dedicated solely to payload deployment, a brief but critical 2-week period.
This is the moment Hera releases its tiny armada. The 2 CubeSats, Milani and Juventus, are carefully deployed into their planned orbits. This requires precise alignment and sequencing to ensure they're stabilized and their communication links are fully operational.
Success here is the difference between getting subsurface data and not.
Exactly. Then we move into the first period of intense measurement. Phase 3, detailed characterization, lasting 4 weeks.
And this is where the core mapping begins in earnest.
It is. Hera starts orbiting closer, performing meter-scale mapping of the entire surfaces. Critically, this is the first ramp-up of the interior exploration. Milani starts delivering detailed compositional data, and the groundbreaking internal structure data from the Juventus Jura radar begins to stream back.
giving us our first look beneath Dimorphos's skin.
Our very first look.
The scientific climax must be Phase 4, close observation, a crucial 6-week period where they risk getting extremely close to the target.
Absolutely. This phase is zeroed in on the effect of the DART impact. It involves high-resolution investigations of a large fraction of Dimorphos's surface, culminating in the AFC cameras achieving that unprecedented 10-centimeter resolution directly over the impact scar.
They'll be able to analyze the precise dimensions of the DART crater.
The dimensions, the ejecta blanket, how the surface materials were physically shocked and altered by that hypervelocity collision, all of it.
And finally, Phase 5, the experimental phase, also 6 weeks long, concludes the primary mission.
This is the operational finale. It's dedicated to final high-risk maneuvers to capture unique, low-altitude vantage points for analysis. And this phase culminates with the planned sacrificial landing of the Juventus CubeSat onto Dimorphos.
That final contact will provide the last piece of unique mechanical data before Hera eventually completes its primary operations.
A fitting end to a 6-month scientific blitz.
So what does this all mean?
It means that Hera is the essential mission that bridges the gap between successful demonstration and reliable engineering. DART provided the proof of concept, but Hera provides the quantitative blueprint.
The actual user manual for deflecting an asteroid.
You could put it that way. The data it will deliver, the accurate mass, the internal structure, the detailed calculation of the momentum enhancement factor, those are the foundational requirements for engineering any future planetary defense missions with confidence.
So we needed DART to show us we could land the punch. We need Hera to tell us exactly what kind of damage that punch does, and more importantly, how to maximize that damage next time.
Exactly. Without Hera's forensic analysis, the deflection factor remains a high-stakes variable based on educated guesses about the target's internal composition.
And this raises a really profound question that Hera is designed to answer. We learned from DART that the impact was far more efficient than predicted, specifically because of the recoil created by the ejected material.
Which suggests that the internal composition, the porosity, the rubble pile nature, is a critical factor in deflection efficiency.
So the asteroid's internal architecture might be the single most important variable for a successful planetary defense mission.
It is, and that's our final provocative thought for you to consider. Hera is carrying the unique radar that will finally map that internal structure. If Hera confirms that high internal porosity guarantees a massive propulsive debris plume and thus a highly successful deflection, what implications does this have for the choice of targets in a real-world scenario?
Do future missions need to prioritize deflection methods based on whether the target is a rubble pile?
Or does Hera's data allow us to engineer solutions efficient enough to handle even solid monolithic asteroids? The answers beamed back in 2027 will redefine the rules of asteroid deflection forever.